Ever wonder how AI models solve problems they've never seen before? Like, how do they figure out new paths when the answer isn't obvious? Today, we're breaking down a study that reveals the secret to smarter AI, how models learn to explore. Let's start with the basics. Imagine training a robot to solve a maze. If you only show it simple paths, it'll get stuck when the maze gets tricky. But what if you teach it to experiment, to try different routes, learn from dead ends, and adjust its strategy? That's exactly what this research did with a 1.7B parameter model, smaller than some big-name AI systems. Here's the clever part. Instead of just throwing the model into hard problems, the researchers used a math trick. They set a token budget, like a limit on how many thinking steps the model could take. For easy problems, they gave it 8,000 tokens. For harder ones, 16,000. But they didn't pick these numbers randomly. They used a special constant, kappa equals 1, 2, to find the perfect balance. It's like giving a student just enough time to think without overwhelming them. What did this achieve? The model didn't just memorize answers, it started chaining asymmetries. Think of it like a puzzle solver who connects different pieces in new ways. For example, it might link algebra to geometry, or use a coding concept to crack a math problem. And here's the kicker. When they tested it with a 32,000 token budget, way more than it was trained on, it beat models with 32B parameters. Smaller? Yes. Smarter? Definitely. But here's where it gets even cooler. Traditional AI methods force models to keep going by adding prompts like wait, like telling a student, keep trying, even if they're stuck. E3 does something different. It lets the model naturally explore longer solutions during training. The result? A 10% performance boost without any extra instructions. Picture a graph showing performance versus token budget. Most models hit a wall after a certain point, but E3's curve keeps rising, slowly but steadily. This isn't about brute force, it's about teaching the model to think more efficiently. So what's the takeaway? Smaller models can outperform bigger ones if they're trained the right way. It's not just about size, it's about how you train them. By combining smart strategies with careful budgeting, E3 shows that AI can learn to explore, adapt, and solve problems in ways we're only just beginning to understand. Next time you see an AI tackle a tough challenge, remember, it might not be the biggest model in the room, but it could be the one that's learned how to think outside the box. Now, let's dive deeper into the mechanics behind this breakthrough. How does E3 actually work? It's built on 3 key ideas. 1. Asymmetries in skills. Think of a model that's great at checking its own work, but not so great at generating answers from scratch. E3 leverages these asymmetries, differences in the model's abilities. For example, it might generate a guess, then verify if it's right. If not, it tries again, using the verification step to guide the next attempt. It's like a detective who tests each clue before moving on. 2. Negative gradients as a guide. Here's where reinforcement learning, RL, kicks in. When a model makes a mistake, E3 uses the negative gradient, a signal that tells it what went wrong. This isn't just about avoiding errors, it's about amplifying exploration. The model learns to try longer, more complex paths, even if they start with wrong answers. It's like a hiker using a map to backtrack and find a better route. 3. Structured exploration with a curriculum. Finally, E3 uses a curriculum to train the model. It starts with simple tasks and gradually introduces harder ones, all while adjusting how much compute the model can use. This ensures the model doesn't get stuck early, like a student who practices easy problems before tackling a tough exam. Let's unpack the math behind one of these ideas, entropy. In AI, entropy measures how uncertain a model's decisions are. Think of it like a robot trying to navigate a maze. If it always takes the same path, it's stuck. But if it's uncertain, if it's exploring different routes, it's more likely to find the exit. That's where entropy comes in. It's the mathematical way to quantify that uncertainty. Now here's the twist. When a model's current best guess for an action is wrong, we want it to explore more. But how do we make that happen? The research shows that using a negative gradient, a mathematical nudge, can actually increase entropy. This means the model becomes more open to trying new actions, even if it's not sure which one is perfect. The model's decisions are shaped by a function called softmax, which turns raw numbers, called logits, into probabilities. The Jacobian of this function tells us how small changes in those logits affect the probabilities. By analyzing this, researchers found that when the model's top choice is incorrect, a negative gradient pushes the probabilities to spread out more, increasing entropy. This is crucial for tasks like extrapolation, when the model has to handle data it's never seen before. Imagine a language model trying to answer a question it's never encountered. If it's too rigid, it might guess wrong. But with this entropy-driven approach, it's more likely to consider a wider range of possibilities, leading to better, more creative solutions. So what's the takeaway? E3 isn't just a technical win, it's a paradigm shift. By teaching models to explore, reason, and adapt, we're moving closer to systems that can tackle real-world problems with human-like flexibility. The next time you see an AI solving a complex puzzle, remember, it might be learning how to think longer, not just think faster.